Okay, welcome back. Our next talk I'm giving with Patrick. This is on OCP hardware management meets PMCI. Quick reintroduction. I'm Hemal. I'm distinguished engineer at Broadcom, and I'm also hardware management project co-lead. I have Patrick here, who is distinguished engineer at Lenovo. In this talk, what we want to cover is in the morning talk, if you were here, we went over the overview of hardware management project. In this talk, what we'll cover is there are some areas where we can further expand the scope of the hardware management project, and that's where we can leverage what we have in DMTF, Platform Management Communication Infrastructure, stands here PMCI, that's the acronym. So that's what this talk is about. And I'll cover the first part, and then I'll hand it to Patrick, who will go over the details of some of these standards, and then we'll summarize. So as you know, OCP hardware management project focus here is to cover hardware management of all OCP platforms. We want to have common manageability across all those. Interoperability is primary focus. As you heard in the first talk and also the talk John Leon gave, it heavily leverages DMTF Redfish for the profile specification. So these are what I call is more external facing interface. Your management client is either talking to a management controller, whether it's a rack management controller or BMC, and that's how the platform manageability is being done via that interface. Then we have within platform what happens, because your platform management subsystem is built of a lot of components, including the BMC, but then there are I/O devices, you have the sensors, there are CPUs, memory, and they all communicate internally, and that's where the PMCI infrastructure comes into picture, and we'll get into that in the next few slides. The way I look at the hardware management project, we have expanded the scope over the years, but there's still one gap where what we can do is for the OCP platforms, we can also come up with a common template, which basically specifies what is the internal infrastructure that you need within the platform. What are the common set of features you need? And there's a case study here that I'll go over, and to give you some idea about what we are talking about. So first, what is PMCI? What is this acronym? It stands for Platform Management Communication Infrastructure. Used to be Component Intercommunication. We recently renamed that to expand the scope. It's all about defining protocols, interfaces for what happens within the box. And box here is like kind of, you can think about a node or a server. Inside the box communication, this is where all these specifications, if you have heard different acronym, MCTP, PLDM, NCSI, as you saw in previous presentation, SPDM, those are all specifications that are produced by this working group. It's been in existence for quite some time. Roots are in desktop. It started with desktop management, slowly it moved to server and at-scale computing kind of management infrastructure. And it's applicable to any system level management or any platform that you can imagine. So what we want to do is leverage the standards that are developed here. We already have an existing case study. There are more specs in OCP where for this type of management features, what internal communication mechanism that you need, they are being standardized around this set of specifications. And we'll see that in a case study, OCP NIC 3.0, which is OCP specification, well mature, and then it's all based on standard manageability, leveraging the standards PMCI had. So first, before I hand it to Patrick, over the years, many volunteers, this is decades of work, including Patrick and I, and there are a number of people sitting in the room here who has contributed. This is what the whole stack is about. And if you look at it from platform management standard, what we have built is the TCP/IP of what you need for platform management. And the reason for building this is there are specific requirements. Within platform, you have devices which are going to be running with very small memory footprint, very limited processing power. So you need to have some common transport which can span all the way from your host software agent to little embedded controller, which is running firmware in 100 KB or less footprint. And that was the conscious thought behind defining all this. So at the transport level, there are two transports, RMII-based transport and MCTP. MCTP stands for Management Component Transport Protocol. So they provide, basically, MCTP gives you physical interface independent transport layer. And there are a number of bindings for the underlying physical layers, as you can see here, SM bus, I2C, PCI VDM, I3C, which was recently added. So this is the layered approach there. And once you have those bindings, then at the topmost layer, you see these upper layer protocols. That's where the control protocol like NCSI, control plane, PLDM, which provides you a number of features, which Patrick will go into detail, but it stands for platform level data model, firmware update, SMBIOS table transfer, to name a few. And then we expanded that further to also include other standards bodies, management interfaces can also run over MCTP. That's where NVMe or MI, this is the management command set that NVMe working group defined. Also recently CXL, fabric management APIs that can be transported over MCTP. And you can also have vendor defined messaging protocol that can run over MCTP. So in a nutshell, this basically forms the basis for that type of within the platform communication. There is a well-defined protocol stack, which is all based on standard. We are working on the next generation of MCTP, but there are significant number of years and the deployment of MCTP, RMII, NCSI, PLDM, and SPDM is one of the recent one that got added. So this is what we want to leverage. I'll hand it to Patrick to go in more details.
Yeah, thanks, Hemal. I think as Hemal described, this whole approach started with something that was intended to be, lightweight, first of all, for the transport layer. That lightweight approach also needed to be extensible. And I think, when you look back over that past decade of all this collaboration that's brought together, all these different bindings and all these different layers of the stack, the extensibility part has really come to fruition here. We continue to see the expansion of all these different command types coming and building on top of MCTP, or MCTP building on top of new physical layers. I3C just as an example more recently. And of course some of the upper layers, you have CXL and some of the FM API and Type 3 CCI command interface that was just recently built in. All of this is really that flexible nature of what that PMCI stack could provide, depending on the exact platform management that you're working on. Again, RMI-based transport, and we'll go through this, that's really available for the NCSI communication. But even if you look at what is PLDM, which is kind of at that upper layer, PLDM could actually be run over either the NCSI and RBT transport, or it can be linked down into MCTP and then one of those physical bindings that are there. PLDM really then expands out that upper layer capabilities, everything from sensor management to firmware update to redfish device enablement. That's all sort of available in the PLDM ecosystem, and you can now do that across either RMII-based transport or MCTP and its physical bindings. And then all of that with some of the security work that was done recently through SPDM, began in PMCI. It's now grown large enough and is extensible in and of itself to many different transports that it's sort of branched down into its own group. Certainly a lot of talks going on here around SPDM in security as well. but you can do SPDM over MCTP, and then through what is known as the secured messages type 6, you can actually encapsulate and encrypt even traditional MCTP, PLDM, or other management traffic like MVM-EMI or those CXL types. So the stack is truly, as I see it, extensible, and it's proven as such through the years as this has continued to adopt new opportunities and new management approaches. So let's just talk a little bit more about each one of these individual interfaces. So starting with NCSI, it's the Network Controller Sideband Interface. Now this is going to be an interoperable sideband connection between the BMC and a network controller. Now at a physical layer, you saw in the previous stack picture, there's kind of a little bit of a blurring of the line between the physical layer and the transport because it's kind of a RMII-based transport. So at the electrical and physical layer, it's based on RMII, but the transport then builds on top of that, and there's some characteristics that drive NCSI messaging and control messages on top of that RBT interface. And that's really what these three traffic types that can be provided over NCSI come into play. The first one is pass-through traffic. That's really where it enables BMC network communication via the NC. It's also sometimes known as sort of like a shared NIC model, where the BMC can have its messages and communication sent out through the shared network interface that the host is also using. Now on packets that are coming ingress, the NC would do filtering and send the packets either destined to the BMC or the host. And that can be set up, and all that filtering and the command response capability of NCSI can actually be set up with the command NCSI messaging layer itself, where you can set up all the request response functions in terms of control configuration. You can get statistics, you can get status, you can get all of that built over NCSI, and you can get that as sort of that second layer of NCSI messaging that you can do over this sideband interface. And then lastly, there are some notification packets. So this is going to be generated by the NC and sent to the MC sort of asynchronously, and they're just going to tell you about certain state change notifications. It can talk about links going up and down, and you can get that asynchronous notification from your NC to the MC through this sideband interface. So that's kind of the one main major attribute of that PMCI stack is really the network controller sideband interface. Now we look at that one that was kind of in the middle, MCTP. It's Management Component Transport Protocol. This is that base transport used for inside the box communication. As you saw, you can have bindings from MCTP to a number of different physical mediums, and that includes SMBus I2C, I3C more recently, PCIe through vendor-defined messages, so typically it's known as the PCI VDM binding. Of course, CXL could also be used, as you can use MCTP over a CXL link, as it's also based on PCI Express, and it's suitable for a wide range of computer platform types. It is operated by a set of endpoint device IDs. So the MCTP is a network of endpoints, all of which can communicate to each other by the assignment of an endpoint ID. There's a construct known as the MCTP bus owner that goes and distributes those endpoint IDs as they are requested. And MCTP allows communication between those endpoints, either kind of datagram approach or request response messaging, depending on whether it's PLDM or just asynchronous events running across that. But MCTP is very flexible and allows all that types of traffic, going from very small packets to aggregating very, very large messages together. All that can be provided by MCTP. There's built-in discovery, so endpoints can discover each other and then start to communicate, peer-to-peer in that way as well. The BMC can go and look at all those devices, as Hemal said, starting with just like 8-bit microcontrollers, all the way scaling up to very powerful, endpoints that can do really complex capabilities and drive lots of different management approaches. And on top of MCTP, that's where the upper layers come in. You can drive, MCTP control itself for PLDM, NCSI, MVM-EMI, SPDM, and again, more recently, CXL management traffic. So this is really kind of that equivalence to that TCP IP type of approach that Hemal mentioned, where it's kind of like just a layering of the stack. So we're kind of moving up the stack here from physical layer into the transport layer. And the next layer up is PLDM, platform level data model. Now this is going to be your data model. It's an effective interface to do a number of different functions that you may need for management. You can do just platform inventory. We have BIOS control and SMBIOS transfer for configuration data capability in PLDM. There's a monitor and control function in PLDM. What that's going to do is provide a set of access to sensors. It could be something just simple like a thermal sensor or other sensors that report statistics. But you're going to be able to get asynchronous events. So thermal is one of those examples we use a lot, right? If something is getting warm and wants to, raise an event, it's able to use a PLDM sensor, and that message can be sent back to an event receiver. It's an asynchronous event that can be sent over PLDM. The event receiver can collect that information and then take action on it if needed. We also have event logging and FRU all built into that platform monitor and control approach as well. More recently, and a little more of the modern years of PLDM, we've built in PLDM for firmware update. Now this allows a standards-based way to transfer a payload from perhaps a BMC down to an endpoint in a way that is standardized, and all of the command and the approaches, including things like when things have to be recovered or restored, you can go ahead and cycle through. There's an entire state machine definition in the specification, and it also defines the package itself. So in a lot of ways, the package has a lot of information around the header, so you can create a PLDM firmware update package that is really consisting of two parts. There's header information, kind of describes a little bit about the information, what version it is, what sort of attributes it might be, applicable to the transfer itself, and then of course the payload. That's going to be what's actually sent down to the device. All of that's done through PLDM, and things like, SPDM could be run, in conjunction with that, and you can have a secured, connection and do all of that together. So a lot of integrating factors within that PMCI ecosystem. Redfish device enablement. Redfish itself, as a Redfish service, is typically an outward-facing interface from a BMC externally to a Redfish client. Redfish device enablement brings that back inside the platform. It maintains that commonality in terms of some of the schema and lightweight approach with a binary encoded JSON packaging, where Redfish inquiries can come into the service provider on the BMC and then continue down to the endpoint, because a lot of times information configuration or firmware updates, et cetera, might need to actually traverse beyond just the BMC. And RDE is really that interconnect that bridges that Redfish service that's outward facing to RDE that's inward facing, and it uses PLDM as well. In the future, we're also going to work on file transfer. That's going to enable large file transfers across the interface. And really, I think in summary, PLDM supports just that variety of different message types, allows messages to be grouped together, so very large messages, again, like firmware update, certainly large payloads. And you're really looking at, if you compare it back to that stack perspective, it's kind of like that layer, 5 to 7 in terms of kind of like that internet TCP IP sort of stack perspective. So you're kind of up in that upper layer here. That's what PLDM provides. So I'm going to turn it back to Hemal now for a case study on OCP NIC 3.0.
Thanks, Patrick. So as Patrick said, he went over, you got preview of NCSI, MCTP, and PLDM. NCSI, basically that covers your sideband communication with NIC, shared NIC model it enables. You can do control and pass-through communication via that. MCTP being a transport, which is the low-level transport that you can use for communication within platform. And PLDM with all this other functionality that can be added on top, which includes the firmware update, Redfish device enablement, SMBIOS, BIOS table transfer. So to put all of that together, when now for the case study, when we started working on OCP NIC 3.0 specification, we took an approach where from the beginning we wanted to leverage if there is something out there. So we first thought about the features. What are the management features this OCP device level specification should specify, which should be common across any implementation. So that's where we looked at a number of things, and out of that came some common use cases that you want to have BMC MAC addresses being provisioned by these devices and being retrieved. You want minimum level of transport where you can do pass-through communication and some control. Then temperature monitoring, which is essential for any board or chip level solution. With the NIC comes all sorts of optical components, transceivers, modules. So you want to also measure their module temperature, inventory of that. And then all of these devices will going to have some level of firmware running, whether it's a control plane, management plane, or data plane. Those firmware, from the management standpoint, you want to know what firmware versions are running on those devices. Get this inventory. Also, you want to make sure that everything that is booted on that device is securely booted, securely updated. And so if you look at it from the use cases standpoint, that's how we thought about these are the features we want. So rather than going off and defining yet another set of protocols, data models to cover that, what you see on this slide is that case study. Once we knew those features, we started looking into what PMCI standards provide, and that pretty much checkbox on all of those. And so based on that, if you see the template, there is a whole section in the spec which primarily defines subset of functionality from the PMCI that is applicable to OCP NIC 3.0. And I have listed a number of those on the slide here. But that's what it means to leverage something that is out there and still have a common manageability standard in the OCP spec. So this is one of the case study. There are also other case study. What I want to do next year is to propose something for the hardware management project. Is going forward, we created this template for the profile and those type of baseline spec in the OCP platform. We want to have similar approach here to start having some kind of prescriptive text in OCP platform specs where you basically refer to this subset of already existing standard to define the set of features or manageability features you want on the platform. You can also do the same for the BMC ecosystem spec where you can specify this BMC implementation that is compliant to this spec will rely on this set of standard for this set of features. And then finally the device level, which I showed the case study previously, where you can put a set of requirements or expectation on these features that if you comply to this OCP spec, these are the expected manageability features which are based on these standards. So this is the main proposal here, is to leverage those existing standard, look at the case study, and then apply it across all OCP specifications. So with that, I'm going to call to action here is basically let's create a template together for PMCA requirements for the OCP spec. With that, we'll stop here. We'll take any questions. There are 2 mics there.
Hemal, one question. In this protocol stack, what kind of resiliency concept we have built in? For example, you send a request, some error happens, and the response doesn't come back, or there's something flipped, some data got corrupted. Is there any resiliency built into this protocol?
Yes, so good question. So question was what kind of resiliency they are built in this protocol stack. So we did pay a lot of attention to that. At the same time, we were sensitive to not really create heavyweight things. So there is some basic packet level drop detection capability, recovery. Higher level have the timeouts and retries that we have defined. So if you go and look at like PLDM, it'll say, okay, these are the number of retries. If you're on this specific medium, then these are the timings you should follow. What is the expected request to response time? When can you declare a request as failed and retry? How many attempts you should do before you do the failure? So That's the kind of resiliency which is already part of the spec. And we continue to look into doing more. Other thing is like when you define the data structure, for example, when we define the table structure, we do protect them by some kind of CRC. So if that transfer is over n number of messages, end to end, you get that kind of integrity check at the end. So that way you can declare the transfer completed successfully.
No other question. Maybe
Sure,
ask
go ahead.
a question. If you want to use this protocol for real-time, you mentioned monitoring is one thing, right? Real-time error reporting, let's say from the host to the BMC, and then pull out to Redfish APIs.
Right.
What kind of fidelity we can get? Like how, is there any limitations on number of events per second that maximum we can allow? Have you done some kind of study like that?
So again, back to most of this functionality is for simply, so like a lot of eventing function and event receiver, the specs will require that you have one event receiver in the system. Now, it can scale. You may allow multiple event receivers to be there. You have to be cognizant of logging functions. There was this other presentation where if you want to retrieve things real time, then of course you need to be on some kind of high-speed interface if you are going to be more responsive, because retrieving, let's say, megabyte worth of log data over SM bus, that's going to take time, right? But like there are PCI VDM, RMII interfaces, which are high speed enough. 100 megabit, like USB 2 is another one we are looking into. So that will allow you to have those kind of real-time of monitoring. Our sensor data model we have in the platform monitoring and control, it is designed to be having that kind of real-time monitoring, where you can poll for event, you can poll for sensor status. Go ahead.
Yeah, I was going to say it's actually optional also to either get asynchronous events or polling, and some physical mediums work better in some ways than others, being able to asynchronous event. So really back to the point, you have flexibility in terms of the physical interconnect. There's going to be some different bandwidth and latency characteristics of which one you use, and then the ability to get the events. You can either do polling and you can poll at various frequencies that you choose to do so, or you can wait for the device to just asynchronously send, which it could do hopefully as fast as it could. So a lot of flexibility in terms of how you want to configure and set it up.
Okay, thank you.
And things we have been talking about on hardware fault management.
Yeah.
For reporting, this may be a very appropriate kind of infrastructure that we can leverage.
This is exactly what I'm thinking right now. So maybe since there is no other question, maybe one more follow-up.
By the way, our next session here, for some reason, the presenters withdrew, so we do have time, so go ahead.
Or maybe I can take offline also.
If you have a question, go ahead.
So if you want to use it for real-time errors, let's say we have a high bandwidth physical media, is there any other bottleneck or any other issues? Or maybe the way question is, and I should rephrase my question is, are there any example implementations where we have used this stack for real-time event monitoring reporting?
Yeah, I mean, I think there are implementations out there that are driving, reporting to the extent of, how much of the logging is there. I use an example of like, thermal events, and I think thermal events, are one that, as fast as you can get it, you can take action. You can start reporting, changing fan speeds, or things like that. So I think there's absolutely, implementations that are out there that I'm certainly aware of that do a lot of that build on this stack and leverage PLDM to kind of wait and get that asynchronous. And again, using those higher speed interfaces like PCI VDM can really have real time to collect more information and more statistics, link down, link up status. I think that's a lot of the information there. So you get into more of the telemetry, maybe more telemetry. We have, of course, RDE that can, bring, redfish type approaches all the way down to the devices and collect it that way and collect large amounts of statistics and data, and you can just aggregate that together into one event receiver as well.
Yeah, all right, thank you.
Any other questions? Okay, so we are going to go on a little bit of break here. We'll resume at 10:40. Thanks, everyone.